So the other time we were doing the hydrostatic equation. Okay, this is a special kind of the hydrostatic equation, but in this particular place we are talking about pressure difference. So we see barometric equation. Okay, so then we got to a point where we're talking about the hydrostatic equation, and we said that we have P plus rho GH, right? Or at times you see this GH and then you see equal to 0, right? Or it can be this way, but they are the same, right? G, and you can even have a Z and you say it's equal to 0. It's all the same thing as talking about the same hydrostatic equation. And then we were saying that for this same hydrostatic equation, we can derive the barometric equation out of it. The only thing that changes is that we replace this P. Okay, so we are saying that this, not just P, is rho actually, sorry. We're saying that this rho is equal to PM on RT. Are you okay? And then we put it in this equation and we end up getting, yeah. We put it in this equation and then we divide by P and then we get this, okay. Yes. We get this. So it becomes the P all on P plus G on RT dz, okay, it's equal to 0. And then when we integrate, we end up getting I won't do the integration here, but this is where like your math application comes in. It's just algebra and then some rearrangement and you get these two equations. Are you okay? But if you want to prove, you can just tell me and then I'll prove it and then upload that one too. So then we end up getting these equations. Are you okay? Yes. So these are the barometric equation. Then again, you see, we had the hydrostatic equation and we said this is equal to 0, right? But here is a case where it has been done for two different cases. You can remember that when we did the hydrostatic equation, we said since it's constant at two different points within the same fluid, it's the same thing. Okay, so you see here, we said it's constant. So like we ended up doing it in two different cases. So you see, we started here and we said it's constant, we moved on and then we created them at two different points. So you see position 1, position 1, position 2, position 2. So you see it's the same thing. Just that in this particular case it has been done for two different positions within the same system. Are we okay? And then we end up getting this. Yes. So this is the barometric equation. The barometric equation is sort of derived from the hydrostatic equation, but then it's applied in the specific scenario. So you see barometric equation, meaning that in this case we are talking about pressure difference. Are you okay? So one typical example is when we are using the manometer. The manometer measures the pressure difference. Instead of doing the calculations manually, so you see we have P plus, I'm writing the hydrostatic equation again, and then we have rho, and then we have G, and then H, right, equal to 0. But if I have two different cases, it will be something like this. We are saying this is constant, right? Remember, we are saying this is constant. Let me just write it out. Constant. Let's see. Right. So if it's constant, I can write it for one position. This is the pressure at position 1. This is pressure P, right? At position 1, this is rho of one of the because we are in the same liquid. Okay, this is a constant, this is a different distance, let's say distance 1, right? I can equate it to pressure at position 2 and I have my rho and I have G, right? Because you have the same liquid, this P here have the same liquid. Because remember when we were talking about this particular diagram, this one, right? And think about this diagram, we said that because all these ones A, B, C, D, E, F, and G, H are on the same like what do you call it, on the same horizontal plane and within the same liquid, the pressure at these points are the same. Okay, so is a similar concept here. So we are saying that we are having the assumption that within the manometer that we are doing the calculations within the same liquid, right? So meaning the pressure at those positions, the density of those liquids are the same within the same position, like different position, like position 1 and position 2. Are you okay? That's what we are doing here. So this one, this G is a constant association to graph. This position 2. Are you okay? So this is equal to this. That's what it's saying. And then when you rearrange this, let me magnify this. When you rearrange this whole thing, if you want to find the pressure difference, okay, because you are seeing the manometers are used to measure pressure difference, right? And then we derive the barometric equation from the hydrostatic equation. So if you are measuring the pressure difference, we just have to rearrange this. We know this density are the same. So if I choose, it doesn't matter. Like irrespective of where you put it, it should be the same. But in the end, you might be seeing some negative and stuff. But the values, in terms as in the magnitude, right? The magnitude of the pressure or whatever should be constant, irrespective of the direction that you choose or which one you choose to put first. Are you okay? But then at times you have to think about it and know which one and then where to put the negative signs and stuff, because it won't be there in the question or something. Okay. So if I choose to bring this P first, that is like I'm finding difference in pressure, right? P1 minus P2 gives me difference in pressure, right? So I'll end up getting, this one is already on the right hand side, so I'll get rho G Z2 minus rho G Z1, right? If I'm rewriting this what's the name, the density is constant, so I bring this one out, I get, and I bring the G out, I get Z2 minus Z1, right? There's it. So it's the same equation that they've rewritten here, and then yeah, it's the same thing. Come on. Yeah. Yeah. So it depends. At times you might be considering any of the quantities to change. So you see in this particular case here, the J is constant. They didn't bring any difference in it. The RM here. So in this particular case, as I was saying, what we are writing here is a general case, okay, but it depends on the scenario they are talking about. So here, P and PB are different. That's the pressure. We are trying to find the pressure difference. Okay, J still remains constant as related to gravity. This RM here is talking about the distance between them. Okay, so it's like they've just written the distance straightforward, like as just one variable. Instead of writing Z1, Z2 as in here, they've just written it out straightforward, trying to tell you the difference in the distance. Are you okay? But the rho, what do you call it? Rho A, rho B here is saying that we are in different positions within the particular liquid. So I hope this diagram, I wish this diagram would have been clearer, so that we see it. This rho A, rho B here is saying that the positions that we are in different liquids. That's why they use rho A, rho B here. But then again, it's still the same concept, doesn't change. The moment you get that the whole thing is from the, what do you call it, the hydrostatic equation, you get to know that it's still the same thing. It doesn't change at all. Get the concept, and then whichever way the question is twisted or the diagram is twisted, you'll be able to answer it. Okay. And then whenever we are doing this barometric equation, we are doing analysis in this particular system, we are considering any pressure that we find, we see is the absolute pressure, meaning that the system is open. In an open system, we have pressure due to atmospheric pressure acting on the whole system, right? So you see here, it says an exposed surface. This is the atmosphere, right? The surrounding of this particular, this is the system. This tube here, U tube here is our system, right? And then the outside here is our surrounding. So meaning the atmospheric pressure is acting on the system. So if you have a system like this, an open system, we see that pressure is acting on the system. So generally we'll be dealing with absolute pressure, meaning that any pressure that we find within the system will be the pressure itself, right? The gauge pressure plus atmospheric pressure. But then again, depends on the system that you are talking about. So you look at the system and make the references, and then anything that you must add or subtract, you see where it's coming from or where it's going. But let me use this. Okay, let's just talk about this diagram. So you see, then again, whenever you are drawing the diagram or whenever you see the diagram, it's trying to communicate with you in a particular way. So you see, whenever you have a region within the diagram, within the system, it's having a particular direction of hatching, it's telling you that we are in a particular field. So you see, from here, I'm just shading it to show. You see that the hatching within that particular field is different, right? So you see, it slants this way. All of it, all here slants in a particular way, telling you that everything here is a particular fluid. Are you okay? So whenever you have an under fluid that's having the same direction of hatching, we can see that even if it's in another position, we can see that it's still in the same diagram. We can see that it's still the same fluid. So you see that here we having the hatching in this way, right, in this direction, and yet we having it in this direction. So we can clearly see that this here, if we are saying this is a fluid, let's say this is a liquid, we can say this is liquid A, and we can also see that this is liquid E. Okay, so if you are trying to represent a diagram in terms of like YouTube or something, when you are doing the barometric equations or barometric analysis, the hatching is very important, okay, because you don't know who will be looking at the diagram. So we just use the hatching, like engineering communication or engineering drawing, to do some communication and show that we are in this fluid, are we okay? Yes, that's what this one show you. So that's just the basic understanding, and you get to see them later. Yeah. Then again, when we come here, we are seeing that the manometer, first of all, we said the manometer is used to measure pressure difference, right? But then a very typical example is that we use it to measure the pressure difference across a orifice. an orifice. Okay, an orifice is a place where like it's like we haven't. So you see, this is like kind of like a tube, right? And the fluid is flowing from here to here, and then it's like we are trying to use something to close. You've placed a particular object. It could be something like this, right, with a hole in it, and then we place it in this particular position of the diagram. But because it's a cross-sectional diagram, that's why they've drawn it that way. Okay. So when it's that way, we are just trying to see that instead of it coming through this bigger area here, so like, let's say initially when it's coming through this side, it's a bigger area. It's like from here to here, right? But when it gets to this particular position, the area here, the cross-sectional area is very small, right? So what do we know? Because we are talking about barometric equation, we are doing barometric analysis, and we are doing pressure difference. Okay, pressure is what? Pressure, let me write it out. Pressure is equal to what? Force per unit area, right? So meaning that whenever we're having a bigger area, meaning we're having a smaller pressure, right? So when we're having a smaller area, meaning a smaller cross-sectional area, meaning we're having a bigger pressure, right? So the whole concept here is that since we are moving from a bigger area here, okay, a bigger area here to a smaller area here, when we measure the pressure difference at this position, right, position A, and we compare it to the pressure at position B, we get to know that the pressure at position B will be bigger. Okay, generally, because we are measuring it at the end of the orifice where we have a smaller area and then the pressure is bigger. Okay, yes, so that's what I'm saying here. Generally, so at this position where we are having, you see the flow is in this direction, this is the arrow, so the flow is coming from here and then it's getting here, right? The position where the flow is coming from, we call it the upstream. Yes, the upstream, that's where it's coming from. And the position where we are getting to, like this part, is called the downstream. Are you okay? Get these terms because at times they'll just write it without diagrams and you have to deduce the whole concept and then know how to find what they're asking you to find. Yes, this is an example. I think we will solve this and then we know what's going. But then again, it's still the same equation, the same concept. Nothing is changing. Okay. So in this particular case, there is kind of like a manometer question. Like the manometer has been used to measure the pressure already and it has been brought out and now we are doing the reading. Okay, so this particular question, right? I'm looking at the left side of the screen. We are here. Okay. For this particular question, it's just saying that this particular manometer here has been used to measure the pressure difference. So it has been used to gauge the pressure already. And there's the reading. But the thing is, like, you see, per engineering drawing, you see that they've shown some what they call truncations here, showing that it's attached to the system and now it has been isolated. This part of the system, of that particular system, has been isolated, so we can see the pressure difference here. Are we okay? Then again, it's still the same question, right? Or the same application from the hydrostatic equation. And then we derive this barometric equation here. Are we okay? So can be written in many ways, as we saw earlier. It can just be the normal one that we wrote out, or it can be in this form. Are you okay? But still the same thing. Nothing has changed. But I think when you remember that static equation, and then you remember that density is equal to what's the name? On RT, P here, and M here, right? And you know what these ones stand for: gas constant, temperature, absolute temperature, pressure, molecular weight. You'll be able to rewrite any one that you want, right? So just remember the hydrostatic equation because the barometric equation is derived from the hydrostatic. So back to the question that we were talking about. Okay, so we talked about orifice and then now we are done with this particular diagram. It's saying that, let me redraw it. So the manometer then again is to measure pressure difference. So it's like we have a tube here, let me just attach it already. So like we have a tube here and then the fluid is flowing, right? Having a particular profile. Then again, you made this profile later on, but I'm just introducing it here. And then we have an orifice here, right? And then we place the barometer here. Forgive me for the diagram, I'm using freehand, so this will happen. I have the manometer here, right? Then again, because this is a small area, the pressure here will be different. Are you okay? So if pressure here is higher, we expect the liquid to go down. But this is just a diagram, okay? We talk about why they've done it that way. Later we'll see what they did to counter what is here. So generally, since here is a smaller area, we are expecting the pressure here to be high, right? So this one will go down. And in the manometer, generally the fluid that is used in the manometer is mercury. So you see, this is the mercury side. I'm shading in a particular orientation. Right, so this is the mercury. I think I should use red because mercury is generally red. So there's the mercury. Okay. Yes. So this one is down here, showing that generally because we're having a small area at this end, we are expecting the pressure here to be bigger, so to push down here more, okay, than here. So that's what's happening. So I'm drawing it, but it's just the same thing. But they are saying that this one is connected to before the orifice, this one is after the orifice, okay. But later on we'll see why. We'll see what they did to counter how they've drawn the diagram, what's happening in this particular diagram. Okay, so this is what's happening. And then they have let me just draw what they've drawn, what is there. So something like this. You have this comes down, right, and then we have this I think Z here. Let me magnify you and see something. This is a particular position, right, and then we have up to here, there's an arrow, and this RM, so meaning that RM here is talking about distance or height, okay. And then this one is up to the surface. This is what's the name, this is ZM, okay. And then we are seeing that this one is the mercury. Let me use red for that one. This one here is the mercury. Wait, yeah, it goes up a bit up to this side. So this one here is the mercury. This one here is the mercury. Yeah, and everything here, because it has been left clear, it can be also left clear without shading it or hatching anything, saying that it's also another fluid. So we are just assuming that the fluid here is another fluid, okay. Yes, that's the communication that I'm showing there. And then we are seeing that there's the pressure. You see, when it's connected at this side, right, there's the pressure here. It gives the pressure here. You see that you are seeing that pressure is A, and you are seeing the pressure here after the orifice is pressure B. Are we okay? And then this fluid here is density of fluid B, and then this right here is density of mercury or fluid A, right? Density of fluid A or density of mercury, right? Whichever way you can write to communicate it, well, fine. No one cares. Are you okay? Yeah. So this is, I think it was position, right? We're using numbers. Yeah. So here's 1, here's 2, here's 3, and here's 4. And this particular position here is 5. So we'll be using this. Okay. And they're saying that liquid A is mercury. Okay. They've given the density, right? They've given the density, and then fluid B flowing through the orifice and filling the manometer leads, okay, is brine. This is the density of brine, and then of that particular brine. When the pressure at the types are equal at the taps, okay. So generally, this is what happens when you're having the manometer without connecting it to any other system. It will be something like this, right? And since we're having the same liquid, since we haven't only the the manometer liquid in it, not any other liquid there, both levels in the, I think, like the legs of the the manometer will be at the same distance, okay. So at the same height relative to the base, okay, or relative to the surface. They'll be at the same height because nothing else is acting on the system. You're having a stable system, a static system, meaning that a system in equilibrium, right? So meaning that at this position we've not connected it to anything to measure the pressure difference. So here and then here are the same height. That's what it's saying. When the pressure at the taps are equal, the level of Hg, that's mercury, in the manometer is below, is 0.9 meters below the orifice tap. So there's the orifice taps. Okay, so then that's what they are saying. Then again, most of the times they won't tell you all this. At times they'll just draw the diagram, or at times they'll just say it, and then you have to deduce how it to be, and then be able to answer the question that they are asking. So there's the first information, and they're saying that under operating conditions. So you see, initially they're saying that when the taps are equal, right, meaning that we are not operating a manometer. It's just saying that it does not be connected to any other external system. Okay, they are equal. But here it's saying that under operating conditions, the gauge pressure at the upstream. Then again, where's the upstream? The upstream is where. So if we're having it in this particular system, and then we're having the flow here. So you see the direction of the flow, right? So this will be our upstream, and here will be our downstream. Are you okay? Let me write this. So downstream, So the thing is just about understanding it and then knowing how to manipulate the whole system that you're talking about. It can change, but when you understand it, you'll be fine, no matter how it's changed. Okay, yeah. So you're saying that under operating condition, meaning that the manometer has been connected to a system to measure pressure difference. Okay, the pressure at the upstream. So let's use this as a diagram. The pressure here is this is 0.14 bar. There's the pressure here. Are you okay? There's PE 0.14 bar. This is PE, right? And then the pressure at the downstream is 250 millimeters of hydrogen. Yes, this is 250 mmHg. Okay. Then again, because we are doing calculations or we're doing calculations in this particular session of the whole course, one important thing is that make sure you are consistent with the unit that you use. So if you are using millimeters of hydrogen, let it be. If you are using bar, let it be. If you are using ATM, let it be throughout. Okay. But because we are doing barometric equations here, generally we want to do our calculations in bar, so we convert anything to bar. Okay. So still we are on the question, just understanding it. Okay. We are still doing this, and they're saying that this is the equation, right? Looking at how it is, they didn't ask us to find anything, right? Okay. So what's the reading? What is the reading of the manometer in milliliters? Millimeters, meaning that we are trying to find distance, right? They've given us the pressure at the upstream, downstream already, and then when you look at the hydrostatic equation, where we have, I'm writing it again, where we have P, and then we have rho, and then G and H, or like distance, right? Vertical distance, which is we see is constant, right here is constant. We've been writing this over and over again because it's very important that you get this. This is basically the hydrostatic equation that we are using the barometric equation, right? We are using in barometric analysis, sorry. Then again, we rewrote this and then we had something like this, and then we said, yes, so we got something like this, right? So looking at it, you've seen that if there's the barometric equation that we are using, this one, let me use red. If this is the one that we are talking about, looking at it, giving pressure at upstream, pressure at downstream, we know the density of both of them, we know acceleration due to gravity. The only thing that we don't know is this, which is the difference in height. So meaning that the reading that they're asking us to find here is the distance, right, between the position that we are talking about. So this all happened. That's what we are finding, right? So we just write that one out. So whenever you are solving questions as such, know the equation you are about to use. Whenever you get the equation that you want to use, then if you want to do any conversion, then you do it. So we haven't P1 here. I'm coming P1 and write the equation again. P2. What's the diagram? I think we use P and PB. So let's do same. So we are consistent with the unit that we are using. Okay, so that will be PA, right? Okay, so that will be PA, PB, and then we have, let me just write it. So we have rho, let me just do this, rho, and then we have G, we have difference in height. Then again, because we are looking for this distance in height, RM, it has already been given in the diagram, so we just use that. Just write the RM out. That will be RM, right? Right. And then we have the density. We are in the same fluid, so this here won't be any density change because we are in the same fluid. It will be just this. It's rho rather, not P. So rho. Okay. So generally, this is what we are trying to find. So we know this. This is the equation that we are using. So we know the pressure upstream, right, is in bar. So which one do you want to use? So in this particular part, they use everything in, they did everything in bar, right? So you see this is the PE, right, at the upstream bar. So you see it's in bar. They are converting it to Pascal. So from the look of things here, they choose to do everything in Pascal. So this is bar. They are changing to Pascal. Times 10 to the power 5. We get the Pascal PA, right? Okay, and then PB. So you see rho GH, what's the name? Pressure. Rho GH is like potential energy, right? Rho GH, and then this PB. This is the density of the brine, right? This is the acceleration due to gravity, and this is the height converted to meters. Are we okay? Because it was given in let me see. Where is it? H. This is something initially. Okay, so what's happening here is that this is what they did. It's even for the pressure B, we're having it in millimeters of hydrogen, right? So meaning that everything that was done here, it was done relative to this one, right? So you see 250, right, millimeters of hydrogen. So that 250 here, we are converting it to meters. That's why we have this. Okay, so millimeters to meters divided by 1,000, and we get this, right? You see, initially when we started, I said generally, if we are having a small area here, we are expecting the pressure here to be higher. So right, so to be able to push the mercury here down, right? This is generally how the diagram should have been, okay? But then it became something like this, and I said we will be explaining it later. So you see that because it's what do you call it? Is it's opposite to the convention that we have per pressure. You see that what happened here is that they brought the negative sign here. Okay, they brought the negative sign here to show that this one, the direction should just change. So like we are swapping the legs of the diagram, right? So what the negative there is trying to say that is that this side of the manometer here should have been here, should come to the left side, right? This is what I'm saying. Okay, that this should have been the left side, and then this should have been the right side of the arm. So like we just swap it. Are we okay? So it should have been something like this. That's what the negative sign is saying. That the arm should have been something like this, and then this should have been the higher side. I'm coming. The higher side here, and this should be the lower side, right? So this should have changed to this. So that's what the negative sign there is trying to say. We are just changing the direction. Okay. So we find pressure at B, and then you see find the difference in these two, difference in density, because we are in different positions, right? We look at the diagram here, position A, right? So because we are dealing with this RM here, right, we are within this RM. We use this particular RM, meaning that we are talking about position 2 and position 4, right? And then within these ones, we are within the density of fluid A and density of fluid B, right? Yes, so that's what's happening. And then we have an density of A and density of fluid B in the equation. Okay. So here, because we are in different position within the fluid, we don't use this just P. It becomes something like this: PA, PB equal to change in density, right? G and then RM. Okay. So this is what we are finding. We've already found this in this one. Like when we have the values for them, we can subtract, and then J is a constant 9.8. This is what we are finding. And then ended up getting this in meters, right? And they change it to millimeters. So that's how it happened. So the negative here, I'm saying this again, is because the diagram goes against or goes in opposite direction to the normal conventions, because there's a smaller orifice, a smaller area, so we're expecting the pressure here to be higher, so it should be able to push the mercury down more than here, right? So that's why they brought this negative here. So should the diagram have been this way, there won't be any negative. The pressure we have will still be the same thing. You can try it out. Yeah. So the next time we'll be continuing here. That's the types of fluid flow and the Reynolds and what do you call it, experiment. There we'll be seeing more of this diagram, like the what do you call it, the velocity profile and the time velocity profile and stuff. So yeah. All right.